Thank you for the introduction and thank you for having me here. So today I want to talk about, I guess, all three topics. MCMC, variational inference, the rivalry and synergy between those two posterior sampling methods, and reverse diffusion Monte Carlo, which makes use of ideas from the diffusion models. How sort of MCMC can help diffusion models and how diffusion model ideas can help MCMC. So when I talk about posterior sampling methods, occasionally people ask me, why do we perform posterior sampling? More often, when I talk about sort of convergence guarantees of MCMC methods, people ask me, why do we care about convergence guarantee? So before answering the how problems, let's maybe answer those why problems first. So why do we do those? Why do we care about their convergence guarantees? And in particular, let's talk about some case studies in sequential decision-making and in differential privacy. Okay, so let's jump right in. And if there's any questions, just feel free to ask me. In terms of sequential decision-making, so by the way, this is joint work with those amazing collaborators. And in terms of sequential decision-making, perhaps the simplest problem is the so-called bandits problem, where you walk into a casino, you see a lot of sort of casino bandits machines or slot machines, right? And each slot machine corresponds to a different reward distribution. Your goal is to maximize the expected reward through repeated play. So in the process, let's say assume that the reward distributions can be parameterized into a parameterization family, theta. Then the goal is through repeated play, we learn more and more about this environment parameterized by theta, right? And at the same time, maximize the cumulative reward. Okay. So reinforcement learning problem is a slightly more complicated, where here, in addition to the actions we can take, for example, on the game console, we also have a state of where the Super Mario is that determines the reward that we can collect. Let's say it's the number of gold coins we can collect, right? For both of those problems, the problem is just to sort of maximize the cumulative expected reward through learning of this parameter theta, which is the parameterizes the environment. Right? So assume that we're given the environment, assume that we know this environmental parameter theta, then what's the right thing to do? So I guess, because let's write first in the bandits environment. So we know that we want to maximize this expected reward, and we know this parameter theta, so we can just estimate the expected reward, right, according to our probabilistic model or generated model, right? And then we just choose an action which maximizes. And if we're in the reinforcement learning environment, basically we just perform dynamic programming to solve a planning problem. That's all. So given the environment, this problem is easy. The question is, if we don't know the environment, what do we do? So a typical idea is through this Thompson sampling method, where we generate a sample of the environment parameter theta according to the posterior of the parameter theta given the observed reward, and then just pretend that this theta is the true parameter, and then perform this optimization problem. So figuratively, this is what it means. So according to each of the choices, let's say we have 4 choices, we formed 4 different posterior distributions of this environmental parameter theta, and then we generate this Monte Carlo sample, right, according to each of those posterior, right? And then conditional on those sampled environments, we perform this sort of we maximize the expected reward, right, and make choices that way. And in most of the cases, this would lead to optimal regret. So this leads to the optimal behavior. Now, intuitively, the reason that this would lead to optimal performance is because of this posterior concentration phenomenon, where if we don't have a lot of data, let's say in round 10, we only collected a few number of data, a few number of rewards, then the posteriors are very spread out, right? In the sense that it would encourage exploration in the face of uncertainty, right? Because we don't know so much about each of those options, And especially for the options we haven't explored, it encourages us to explore more. But as we collect more and more data points, the posteriors becomes more and more separated, right, and more concentrated. So then eventually it would fixate on the right choice because the posteriors are entirely separated from each other. So the expected reward it's clearly that one is always better than the other. So this kind of posterior concentration phenomena gives us this optimal guarantees for Thompson sampling. But so operationally, there is this problem that the posterior distributions, oftentimes they're complicated. Right? We can't just directly sample from it. So instead, we would have to appeal to approximate sampling, right? Let's say in round n, we'd have to sample approximately according to the posterior distribution. And now the question becomes, for approximate samples, what kind of guarantees do we need? Right? So that the sort of appealing optimal performance is guaranteed. So this is why oftentimes we do need some theoretical understanding of how well our approximate Monte Carlo sampler works. And in the case of sequential decision making, it turns out that we don't really need the posterior distribution to be that accurate in terms of, let's say, total variation distance or KL divergence. Instead, what we really need is the tailed behaviors to match because we want to keep this posterior concentration phenomena. And in mathematically, what that means is that we want its sort of Wallerstein-Q's moment, Wallerstein-Q's distance to sort of match up to the square root of Q order. And we want it to shrink according to the number of samples we have, in the sense that the more concentrated those posteriors are, the more accurate we want it to be. But initially, the error can be huge. So essentially what that means is that we want roughly they would have matching Q's moment, and the error tolerance scales like square root of Q. So the higher the moment there is, the larger tolerance we can afford. So that's one example where we want sort of a bespoke convergence guarantee, right, for our approximate sampler for this sequential decision making problem. And in another case, we can also think about, okay, can we use the Monte Carlo approach for differential privacy? Because inherently, for differential private questions, we want the queries to be random so that the adversarial cannot figure out what's going on in the data set, right? So typically, the statement of differential privacy goes as follows. For a randomized algorithm, the epsilon delta approximate differential privacy means that it goes in the sort of hypothesis testing statement, essentially saying that if the data set differs by one data point, and then another adversarial want to test whether the data point actually changed, then without looking at the delta, what happens is that this epsilon differential privacy tells us that epsilon is the sort of optimal confidence or optimal statistical power an adversarial can possibly get, right? That one data point indeed changed. Okay, so all is well and good when delta is equal to 0, right? So essentially that just means however we change the data set, the adversarial cannot figure out with 100% confidence that the data set indeed has changed, right? As long as epsilon is finite. But the problem happens when there is this non-zero delta, right? Which essentially means that with this delta probability, there is a case where the adversarial will be able to figure out with 100% confidence, right, that the data set indeed changed, right? So this represents arbitrarily severe privacy leakage. Essentially, it's as good as, with this delta probability, your data is released online. Right? So there's nothing guaranteeing against that. So of course, it would be appealing to remove this delta, right? So the question is, can we achieve this pure epsilon 0 differential privacy? So if we think about this problem from a posterior sampling perspective, right? So let's say if what the algorithm does is generate a sample according to the posterior, right? And once we have the posterior sample, we can do post-processing, we can do forecasting, conditioning on the posterior sample, right? So, but if let's say this algorithm is performing posterior sampling, let's think about how this would work, right? Whether it would guarantee pure differential privacy. So if we perform this, then we would know that this e to the sort of epsilon privacy would scale according to the posterior density ratio when we change one data point, right? And there wouldn't be any delta here. The delta is 0. And as long as the log posterior is Lipschitz continuity in the data, then epsilon would be smaller than the Lipschitz continuity of log posterior, right? So it seems like we can get pure differential privacy for free. And there's no sort of approximation here. Of course, the problem is if we cannot directly sample according to a posterior, if instead we have to sample according to an approximate posterior, then if the TV distance, total variation distance, from the approximate distribution to the posterior has a small error, then in terms of the total variation distance, then we would recover this approximation delta. So it would sort of degenerate into the approximate differential privacy. So the question is, what kind of guarantees do we need so that we can maintain pure differential privacy? And what it turns out is that if we can guarantee Wallerstein infinity distance, then adding a small Laplacian noise to the algorithm would guarantee us the pure differential privacy. Okay. So in this case, what happens is that we'll need a sort of more accurate sort of MCMC sampling algorithm. For example, the Metropolis-Hastings suggested algorithm that would help us to achieve that. But any questions till this point?
Sorry, just ask for the notation. Can you remind me what's Wasserstein infinity distance?
Right. So essentially, that means so there exists a coupling so that sort of the essential supremum of the distance moved from one sort of distribution to the other in terms of their samples is bound. So essentially, that means the tail have to exactly match. If there's anything that doesn't match in the tail, then that would incur an infinite Wasserstein infinity distance.
So that's stronger than any like Wasserstein K distance.
It's the strongest.
Okay. Yeah. Thanks a lot.
Right. So this says to the point that to be able to apply our MCM Monte Carlo algorithms in the wild, in practice, we do need some theoretical understanding of them, and oftentimes the requirements differs in terms of the downstream applications. Okay, so after talking about the why problems, then let's talk about the how problems, and let's talk about the rivalry and the synergy between MCMC and variational inference. Okay. So this problem is motivated by the following folklore, which says that variational inference is fast but biased, and MCMC is unbiased but slow. So even since I'm working on the MCMC problems during grad school, I've been wondering sort of how true is this statement. And the focus will be on the scalability of the algorithms, how the convergence rate scales to various problem complexity. In particular, we'll focus on the dimension dependence when the model grows in dimensionality. And we'll take an optimization point of view so that we'll achieve a non-asymptotic analysis so that we can take into account the bias that the variational inference incurs and compare variational inference against the MCMC on fair grounds. Okay, so let's talk briefly about the setting of the problem, although I assume most of the audience are familiar. So let's say that we have a posterior distribution we want to generate samples from. And theta is the parameter space, d is the observations, which is proportional to the prior times the likelihood. And we want to generate samples to approach a high-dimensional posterior distributions. So we want to generate a sequence of those samples where it gets more and more distributed closer and closer to the target distribution, to the posterior. So we'll focus on the algorithmic complexity in the sense that how many times we need to iterate until our sort of our sample is close enough to the posterior, right? So our hope is that PK will approach P star as K grows larger, and we want the approach to be fast. Right? And in terms of optimization, this essentially means that we want to minimize some kind of divergence or sometimes kind of a distance from the current distribution PK to the target distribution P star. Right? And we can use, for example, the Kohlberg-Liebler divergence as the optimization objective. So this is just optimization in the space of probabilities. Right? And if we think about optimization, I guess a lot of times in Euclidean space, what we can think about to optimize a certain objective function is just the gradient descent type of method. So essentially it just updates according to the negative gradient direction. And figuratively, it looks like the following. Now, on the space of probabilities, then I guess the first question is figure out, what's the gradient with respect to the KL divergence on the space of probabilities. So in the Wallenstein 2 metric space, the gradient of this KL divergence becomes conveniently represented on the space of samples as a vector field, right? And the vector field can be computed as gradient with respect to theta of the log current distribution over the target. So then for each sample following the current distribution, in some sense, we can just update it, right, according to this negative gradient field. Right, so it seems like this directly solves the Monte Carlo problem, and there isn't any more problem to solve. But there is a caveat, right? We can't directly implement it because for P star we know it up to a normalization constant, but PK oftentimes we don't know, right? We have samples according to PK, but to use samples to directly approximate it, it's a density estimation problem and it's NP hard, right? So oftentimes we can't directly use this formula to update. Now, this separates into 3 approaches, which represent 3 different categories of algorithms. So one approach is that we'll parameterize PK using a parameterization family, right? And this is a variational inference. So we would map the gradient on the space over the probability distribution to the gradient of the parameters, right? So we'll map one tangent space to a different one and allow for some bias. And another way is that we can consider using an equivalent process with rather than gradient of log PK, right? So for example, in the continuous limit, this term is equivalent to the adding Gaussian random noise, right? So then we can replace this by looking at, so the gradient over the log target distribution plus Gaussian random noise, right? Or making use of this notation, this becomes just, gradient descent plus Gaussian, appropriate amount of Gaussian random noise. And this corresponds to Langevin MCMC. Figuratively, it roughly goes down the hill, but also has this Gaussian random noise kicking it around, capturing the variance. And for the third method, we'll talk about it later. Now the question becomes, how do we compare those 2 classes of method? Right? So in terms of the variational inference and MCMC in terms of their convergence rate. So if we directly look at the experimental result, this is typically what it looks like. So if we use MCMC, the Langevin type of method, so sort of it goes towards the end, right? But it's slightly slower than variational inference, using, for example, gradient descent or stochastic gradient descent. Right? But oftentimes when we look at this picture, sort of the y-axis is oftentimes the sort of the standard deviation estimate which only estimates the self-correlation and sort of neglects the cross-correlation among different covariates. So this isn't really a fair comparison to some extent. And instead, what we should actually look at is when they're bringing to the same standard, sort of how do their convergence guarantees compare against each other? And it's hard to verify in experiment because estimating the cross correlation is kind of hard. So instead, having some theory is useful. So let's first consider, let's say, the simplest case, the strongly convex and Lipschitz smooth objective functions, and then look at posterior distribution that's distributed according to e to the negative objective. In those cases, it is well known that the Langevin algorithm's convergence scales only linearly with respect to the dimensionality of the problem. But instead, if we consider the gradient descent-based black box variational inference, and if we further sort of assume that the objective function is quadratic to remove all the possible bias, and it is also strongly convex and Lipschitz smooth, then what happens is if we apply stochastic gradient descent black box variation inference, then the complexity, algorithmic complexity, scales as dimensionality squared. Here, black box variational inference means that even though in the theory we assume that the objective function is quadratic, we don't assume that the algorithm knows it. Okay? The algorithm can only query gradients of the objective function. So there seems to be a dichotomy, right? So it seems weird that experimentally people claim that BBVI is faster, but in theoretical analysis, it seems like it's even slower. So what happened here? I guess for the Langevin algorithms analysis, people would rather know how it goes. So let's maybe open the box for analyzing the black box variational inference a little bit and see and get some intuition of why this analysis is the case. So first of all, what we realize is that if we need to capture convergence in terms of Kovac-Liebler divergence, so that they are on the same ground, then for variational inference, we really need to capture the covariance structure. Otherwise, KL divergence blows up. So in that case, let's say that we parameterize the Gaussian variational family using the precision matrix. Then the algorithm boils down to taking gradient descent of the KL divergence with respect to the precision matrix. And if we write it out a little bit, then what happens is that it becomes expectation of the gradient with respect to the precision matrix of the variational family times the logarithmic ratio between the sort of approximate distribution and the target one. Okay. So the part that's only involving the approximate distribution is fine because we parameterize it using a Gaussian family. We can just estimate it because the estimation distribution is also from a Gaussian family. So this is explicit. The problem occurs when it also involves the posterior distribution. Because we don't assume that we know the form of the posterior distribution, we can only query using samples to query it. So here there will be statistical estimation error, right? So we need to use samples to estimate. And using samples to estimate it incurs error. So then the question is, okay, so then what's the variance of this statistical estimator? So if we just use samples according to posterior distribution to estimate it, we know that the convergence rate of stochastic gradient descent is constrained by the stochastic gradient variance. And then if we study the variance, assuming that the variational family is Gaussian, and also assuming that the posterior is Gaussian, then what happens is that this is estimation of a fourth order term, and the stochastic gradient variance will scale as dimension squared. And that's where this dimension, dependence on the dimension squared comes from. Okay? But of course, for variational inference, there is one benefit in the sense that if we can get lots of parallel compute, let's say we have a million machines. Then what happens is then this expectation can be done in parallel. So this query to the posterior can be done in parallel. So it does offer some additional flexibility, right, in the sense that it can trade a parallel computation for convergence time. If, let's say, the number of machines we can allocate is scales like D, then the convergence times, scales will scale linearly with respect to the dimensionality. Now, from a computation complexity point of view, we can so here then let's maybe go back a little bit and see that, okay, so intuitively, or on a higher level, why in terms of computation complexity, there should be an additional D, or is this just an artifact of the algorithm design? So to some extent, if we have solved this black box variational inference problem, then we can directly read off the covariance or the precision matrix, right, directly from the converged result. But instead, if we want MCMC algorithm, if we want samples according to MCMC algorithm to provide us with the covariance or the precision matrix, we need about D number of samples to be able to estimate the covariance matrix. So to some extent, they are comparable to each other. Right? It's just in terms of providing a sample, black box variational inference is kind of sort of overkill, right? It's doing something that's not really needed. Okay. But in terms of the total computation complexity, they're comparable. Right now, then the question becomes, okay, if we just want a sample, right, according to a posterior distribution, can we cut corners for the variational inference? Can we maybe consider a more restrictive parameterization to accelerate computation? For example, one idea might be, can we use a diagonal plus low rank structure to parameterize our precision matrix? So then we don't capture the entire posterior correlation structure. We just capture part of it. Like, could this accelerate the convergence? Now, it turns out that we can, in the sense that if we only incur P number of low rank structures, then the gradient variance reduces to P times D. So then if P is finite, then we only need linear in terms of dimensionality, so that we would have convergence. And the entire result looks like the following, where here there's this optimization error, where delta is the accuracy level we want to get to. So we can see that for sort of any sort of accuracy level in terms of this term, the number of K, the number of gradient queries we need, scales linearly with respect to D, and then linearly with the number of the low rank components we want to take into account. And this is the approximation error, or statistical error, approximation error, where for all the sort of terms that are not taken into account, there is this bias, right? So lambda star means the eigenvalues of the true precision matrix. Okay, so then, figuratively, this is what the trade-off looks like. So if you look at the convergence curves, when rank is smaller, let's say 2, the convergence is instant, but there is a large bias. And when rank is higher, the convergence is slower, but it converges to a better place, right? And let's say if the true rank is 64, then you would see that the increasing the rank slows down the convergence, and they converge to the same place. Now the question becomes: this seems to provide us with a sort of Bayesian model selection problem, in the sense that what's the optimal rank given certain assumptions on the data structure, right? So assuming that the true precision sort of eigenvalue has a power law spectrum decay, then what happens is then we can choose this optimal rank adaptively according to the power law, how the power law decays. And then under this choice, the sort of query complexity is always scales linearly with respect to the dimensionality of the problem, okay, under this optimal choice. So as long as there is a power law decay for more than a half order. So then this seems to suggest that there is a dimension-free MCMC method in those cases, right? Whenever there is a power law decay in the precision spectrum. And that is when sort of Tongzhang started to asking me the following question. He says that convergence optimization converges, the convex optimization converges dimension independently. Can Langevin algorithms convergence time be dimension independent in RD as well? Because I was explaining to him that why there is a dimension dependence in the Langevin algorithms, and he didn't think that it makes sense. So we started working on this. So it turns out that if we take a composite optimization perspective, then it is indeed possible to make the convergence time of Langevin algorithm also dimension independent. So the rationale is the following. So we can decompose, let's say, the KO divergence objective into two parts. Right? One part is the self entropy, another part is the cross entropy. And so what happens in the Langevin algorithm is that we can decompose this Langevin algorithm of gradient descent plus Gaussian random noise into two parts. One part is just gradient descent, which is doing gradient descent on the cross entropy, actually, on the space of probabilities. And then another part is just adding Gaussian random noise, which is performing gradient flow on the self entropy. Okay. And so we compose all those. Taking a composite optimization point of view and analyzing first adding Gaussian random noise and then performing gradient descent, aligning the objectives, we actually found that, okay, it is indeed possible, assuming that the objective function is strongly convex, and also its Hessian is upper bounded by strong convexity component plus a sort of, let's say, plus another component. And if we assume that the Langevin algorithm is initialized correctly, then actually the convergence rate would only depend on trace of this additional Hessian square. So if we go back to the variational inference result, so this part is finite and does not depend on the dimensionality D when actually the trace of the Hessian square is bounded. So this implies that there will be no explicit dimension dependence under the same condition. So it seems like MCMC provided new perspective for variational inference, and variational inference in turn provided sort of improvements and new perspectives to MCMC algorithms. Okay, any questions to this part?
Sir, so could you, so I'm trying to understand the condition here. So U here is the negative log density of the gradient.
Yes.
And so to say that it's less than mi plus h, so how large is this h typically in?
Right. So h. So here, let's say h is arbitrary.
Okay.
Then what happens is then trace of the h square. If we don't have any additional assumptions, it will scale linearly with dimensionality. Right? But here, if we go back to the assumptions in variational inference and look at the cases where the eigenvalues of h has a power law decay of at least a half order, then what happens is then trace of the h square would scale like a constant.
I see.
So this exactly matched the case in variational inference. Right? So if there is low rank structure plus a diagonal, then the convergence rate shouldn't depend on the dimensionality.
Okay, thank you.
May I also ask whether we have already know some kind of query complexity lower bound for different sort of variational inference algorithms?
Actually, analysis of variational inference algorithm is very limited. So yeah, I think this is an interesting question, but not a lot of people worked on it.
Yeah, thank you.
Okay. Okay, so then we can also think about, okay, so then what if we have multimodal or long-tailed distributions? So how can we make use of some of the new methods to deal with it, right? To help with that? So we'll talk about how we can make use of ideas from diffusion models, particularly making use of the reverse diffusion process to help Monte Carlo problems. And then we'll also talk about how to use MCMC to accelerate the inference of diffusion models. So we see that, okay, so if we initialize from, let's say, a standard normal up to the current distribution, and then up to some, and then stop at some distribution, hopefully it's close to the target distribution. Roughly, we can think about tracking this gradient descent type of dynamics. And the difficulty is parameterizing or learning this gradient of log current distribution. Right? So currently, if we think about diffusion models, one idea is to directly parameterize this called the gradient of log current distribution as a score function, right, and learn it. So we tried it. So it didn't really work. The reason is that it's really hard to obtain an accurate estimation of the score function along this sort of forward gradient descent dynamics. So we tried to look for what could be the possible reasons for that. So one reason is the following. So if we look at this forward diffusion process, right, diffusing from a standard normal to a complicated target distribution, and in this case, let's say it's just an even mixture of Gaussians. In the intermediary, we find that actually those structures are even more complicated than where it's supposed to converge at, right? Because you have this sort of mixing phenomena. So in the middle, those intermediary distributions have all those sort of triangular shapes and so forth. It doesn't really appear in the posterior or in the initial distribution. So to some extent, parameterizing the intermediary score functions is kind of an overkill, right, to be able to just generate samples from the posterior. Now the question is, okay, can we make it simpler? Right? Can we avoid this, parameterizing the entire procedure, the entire process? One idea is to start at the end, right? Start at the posterior distribution and then go backward towards the standard normal. And in terms of the updates, this directly looks simpler in the sense that previously we had the gradient log of the posterior on the denominator, and here gradient log of a standard normal is a linear term, right? So essentially we turned a nonlinear term into a linear term. So algebraically, this already looks simpler. And then what we need to do is to estimate the scores in the middle and then invert the process or revert the process. Okay, so let's look figuratively what happens. Right? If we start at the target posterior, an even mixture of Gaussians, and then let it diffuse back towards the standard normal, then all the intermediary distributions are just uniform mixtures of Gaussians. So, right, to be more exact, they're all just Gaussian convolutions of the target posterior. So it doesn't introduce any additional information that is needed, right, to generate samples according to the target distribution. So this looks promising. Right? Now, the elephant in the room is how do we actually estimate the score function? Right? How do we estimate it? It turns out that the score functions are explicitly computable in the sense that the score functions are just expectations with respect to a linear term. Right? Everything else is constant. And the sort of approximating distribution is the posterior multiplying a Gaussian. So that's all we need to do. So we need to just, in every intermediary step, what we need to do is to perform a mean estimation of a distribution that's posterior multiplying Gaussian. So intuitively, or maybe the first idea that's probably on top of everyone's head is, okay, so this is a posterior times Gaussian, so why don't we do importance weight sampling, right? We just sample according to a Gaussian, and then do an importance weight which is the posterior multiplying a linear term. And it directly gives us an algorithm. So we tried that. I guess the downside is that empirically, the downside is the variance is large in this empirical weight sampling procedure. And theoretically, if we want accurate samples, then the sample complexity scales exponentially with the dimensionality. Okay, so a more low variance estimator is actually if we use Langevin algorithm to perform the Langevin algorithm on the posterior multiplying a Gaussian. That's actually a much lower variance algorithm. And we can treat this Gaussian term or a quadratic term as a regularizer. So, and if we look at the coefficient a little more closely, when t is smaller, when we are closer to the target distribution, the denominator becomes 0, and this regularizer blows up. So basically, this regularizer will dominate when t is small. And so basically, this qt is simple to sample from, like when t is small. More accurately, when t scales like 1 over the Lipschitzness of the sort of the Lipschitz smoothness of the posterior distribution, then the regularizer will always dominate. So then this objective is always strongly convex, or this distribution we want to sample from is always strongly log concave. So that's a simple problem for Langevin MCMC. And of course, when t is really large, then this approximate distribution is simple. But the problem is, okay, there's a gap in between, right? How do we bridge this gap? So we know that reverse diffusion Monte Carlo is simple when we're close to the posterior, but the rest of it we don't know much. So a simple answer is why don't we don't do any of the rest? Why don't we just set this point as the new target, do a recursive call to the entire algorithm? Right? Essentially, we only do anything when it's simple to do, and everything else we throw it into the recursion. Right? So we segment, effectively, we're segmenting the time axis into k number of segments. And in each segment, we perform a simple task. Okay, and so here for the second segment, for the first segment, we just do the simplest task and then do a recursive call to the second segment. For the second segment, the target distribution now is different. It's not the posterior now. It's the posterior essentially convoluted with a Gaussian now. So in the case segment, algebraically, this is what it looks like. So we move the target to the nearest end checkpoint, and so that the t minus the nearest checkpoint is always small enough, so then it's always a strongly convex problem, right? And then to be able to get gradient with respect to the checkpoint, we incur a recursive call to the next segment. And we solve recursively for the scores. Okay. So figuratively, this is what it looks like. So in each segment, we need to sample from Qt a number of sample points to be able to estimate the score at PT. And then for each of the sample points, we need a group of samples to estimate the score according to it. And for each of the sample, we do that, recursively call it. So obviously, this would depend exponentially on the number of segments there is. But the number of segments would scale, as the Lipschitz smoothness or the Lipschitz continuity of the scores times the logarithmic, times terms that are logarithmically dependent on everything else. Okay. And exponential dependence on the Lipschitzness, I don't think it can be avoided anyway. Okay, so we tried it on a multi-modal posterior distribution, and the experimental results looks like the following. So when the mode spreads are small, then what happens is then everything looks similar. But when the mode spread increases, then Langevin algorithms kind of starts to flatline. Basically, it doesn't do anything in a short amount of time. But reverse diffusion Monte Carlo still sort of converges relatively quickly. And we can prove that MCMC convergence time scales exponentially with the mode spread, and reverse diffusion Monte Carlo reduces this exponent beyond the MCMC lower bound. So essentially, it can reduce the exponent more than any of those MCMC methods. And in terms of broader application, we can also talk about the total computation complexity under two assumptions. One is that we assume that the scores are Lipschitz continuous, and also assume that the posterior has second bounded moment, second order moment bound. Then reverse diffusion Monte Carlo convergence will scale exponentially with respect to the Lipschitzness of the score, and then quasi-polynomially with everything else. Okay, so if we compare it to MCMC algorithm, so in the case of long-tailed distributions, actually those two assumptions can still be satisfied. But for MCMC, for example, if we use log Sobler for other isoparametric inequalities, actually they no longer hold, which essentially means that sort of this reverse diffusion Monte Carlo expands the horizon of applicable Monte Carlo algorithms to a more broader class of algorithms. So you can actually have provable convergence in those cases. Okay, any questions about this?
Sorry, I think I understand the several pieces of your presentation, but can you maybe summarize a little bit how the algorithm overall goes?
Right. So in terms of the algorithm implementation, so what happens is then, so in each segment, we perform the Lagrange MCMC to generate a sample, generate a number of samples according to the sort of the distribution QT. And then, so use those samples to perform a mean estimator to obtain the score function, right? And of course, those samples, to be able to generate those samples, it depends on having gradient queries to the previous segment's score. So we recursively call that.
But in the first place, you already need sample from the posterior, or
Right. So in the first or last segment, we directly have gradient of the log posterior.
Oh.
Right. So basically, after expanding the recursion, the last step is the posterior.
Yeah, thank you.
Okay. Now, we can also talk about flipping this idea, right? Can we use reverse diffusion Monte Carlo or use MCMC to accelerate the inference in diffusion models? So in this case, the setting is a little different than typical Monte Carlo problem. Basically, given the data samples, according to, let's say, the data distributions, we don't know the data distribution explicitly, but we have samples according to it. We want to generate more samples, right? And how do we do that? So in that case, sort of the forward process is a process going from data to noise, just as what we had in reverse diffusion Monte Carlo. And it looks like the following, right? You gradually add noise so that the data gets corrupted into noise. And then in the reverse process, we go back from noise to data, making use of the score function. Right? And this is typically what DDPM does, the popular diffusion model does. Right? And what happens in this case is, if we can somehow reduce the number of intermediary steps that goes from the data to noise and also goes from the noise to data, then we can reduce the inference complexity of generating a picture from noise. The question is, how do we do that? How do we achieve that by, for example, making larger jumps and reducing the number of jumps in between? So one idea is to basically consider transition kernels, consider jump processes, right, instead of those stochastic differential equations. So the forward transition, if we rewrite it, actually it can be expressed as a transition kernel, right, with a Gaussian transition kernel, conditional on the previous distribution, the Gaussian transition kernel convolutes on it, and then goes into the next step. And we found that the reverse transition kernel is also easily representable, which is essentially, incorporating the score information into this Gaussian transition, and this becomes the reverse transition kernel. So as long as we can simulate or generate samples according to this reverse transition kernel, we kind of solve this problem, and we can take arbitrarily large steps, right? We can take arbitrarily large jumps and reduce the number of steps however we want. Okay, so now the key becomes, how do we generate samples according to this reverse transition kernel? So in the inference step T, we want to draw those samples, and how large can each step be so that this reverse transition kernel can still be simulated, right? This algorithm can still be implemented. Now, this becomes, I think, this similar to what we discussed before, right? So this transition kernel will be strongly log concave if t prime minus t is small enough so that this term will dominate. So, and then this is also easy to sample from, according to MCMC. So we can directly make use of the results from the reverse diffusion Monte Carlo to help us sort of accelerate the diffusion model inference. So if we directly use DDPM, the popular algorithms out there, the step size it needs to obtain epsilon accuracy in terms of convergence scales like epsilon over Lipschitzness times dimensionality. And in turn, this gives us a total computation complexity of Lipschitzness squared times dimensionality over epsilon. So it takes this number of steps to obtain epsilon accuracy. And here, the outer loop complexity scales linearly with Lipschitzness. And now it boils down to what's the inner loop complexity for sampling according to MCMC. So if we directly just use Langevin algorithm, then what happens is then it's actually equivalent to just directly doing DDPM. So we'll see that with vanilla Langevin algorithm, inner loop complexity scales like d over epsilon, and then taking into account the error accumulation, then actually the computation complexity, total computation complexity is comparable to DDPM. But since we can design any of those inner loop algorithms with MCMC for strongly log concave distributions, we can use, for example, accelerated Langevin algorithm, which improves dimension dependence to being square root of d instead of linear in d, right? We can also consider, if we care about epsilon dependence, accuracy dependence, we can also consider Marshall plus Hastings type of algorithm, which improves the accuracy dependence to being log of 1 over epsilon. So there are many more MCMC algorithms, MCMC techniques that can be applied to accelerate the convergence, the inference time of diffusion model. So I guess this concludes my talk, and thank you for your attention.
Okay, yeah, thank you so much for the very nice talk. I will stop recording now and